Interpreting nuclear magnetic resonance (NMR) spectra is an essential skill in organic chemistry and structural biology. NMR spectroscopy provides information about the structure and environment of atoms in a molecule by measuring their magnetic properties. Here's a general guide on how to interpret NMR spectra. Understand the basics. 1. Nuclei with a non-zero magnetic moment, such as hydrogen, H, and carbon-13, cubed C, are commonly studied in NMR spectroscopy. 2. NMR spectra display signals as peaks on a graph. 2. The x-axis represents the chemical shift, delta, in parts per million, ppm, while the y-axis represents the signal intensity. Identify the number of signals. 1. Each distinct set of chemically equivalent nuclei in a molecule will produce a separate NMR signal. 2. Count the number of different types of hydrogen or carbon atoms in the molecule. 2. Each type corresponds to a unique signal. Determine chemical shifts. 1. Chemical shift, delta, indicates the location of a signal on the NMR spectrum and is expressed in ppm. 2. Chemical shifts are influenced by the local electronic environment of the nucleus. 3. Common chemical shifts for hydrogen atoms. Alkyl, carbon trihydride, CH, 0.52.0 ppm. Aromatic, ARH, 6.09.0 ppm. Aldehyde, CHOH, 9.010.0 ppm. Carboxylic acid, COOHH, 10.512.0 ppm. Analyze signal splitting. 1. Signals are often split into multiplets due to the coupling of neighboring nuclei. 2. The number of peaks in a multiplet indicates the number of adjacent, non-equivalent hydrogen atoms, N+1 rule. 3. The splitting pattern, e.g., doublet, triplet, quartet, reveals the relative number of adjacent hydrogens. Integrate signal areas. 1. Integration involves measuring the area under each signal peak. 1. It gives the relative number of hydrogens responsible for that signal. 2. The integration ratio of different signals can provide insights into the mole ratio of different types of hydrogen atoms in the compound. Analyze spin-spin coupling constants, J values. 1. J values indicate the strength of coupling between adjacent nuclei. 2. The distance between the peaks in a multiplet is proportional to the J value. 3. Larger J values lead to wider separations between peaks. Consider the molecular structure. 1. Use the information obtained from chemical shifts, signal splitting, and J values to deduce the connectivity and arrangement of atoms within the molecule. 2. Consider functional groups, symmetry, and possible isomers when interpreting complex spectra. Verify the assignment. 1. Compare your interpretation with known data, databases, or spectral libraries to confirm your assignments. Practice. 1. NMR interpretation improves with practice. 1. Work on a variety of NMR spectra to hone your skills. Remember that interpreting NMR spectra can be challenging, especially for complex molecules. It requires a good understanding of NMR theory and the ability to apply that knowledge to real-world compounds.